name is Sergey Kachkin. I'm working in the troll company. I'm an engineer, and I will be speaking about performance. So it's quite a wide area, and insufficient performance is a problem for many employees. For example, developers and testers. So different tasks, and architect plans the system for the future loads and performance keys, engineers. All these people have different competences and they require different utilities, and all of them are facing the problem of performance. So it can be a long talk. I will dwell upon one type of tasks, and I will be speaking about the most popular troubleshooting tools in terms of performance improvement. So I'm not related to the company which accumulated quite a vast experience, but I will share this experience with you anyway. So I uphold the following point of view. System engineer, maintenance engineer, so performance consultant, all these people solve similar tasks. It means that you are sitting somewhere in a cozy place, doing something important, and a customer calls you and complains about a slow performance. So your task will be to solve the problem, to find the right way. So even it's not your task technically, it's always useful for you to get some new experience. So how to describe the problem? Usually the problem is very poorly described, so it's quite difficult to understand what exactly is slow. Quite often you will be given some subjective point of view instead of some objective parameters. So very difficult it is to translate all this into the language of the system. So actually it's not a problem of people, but a problem of metrics, because they become obsolete. So you usually work with production environment, and it's not recommended to slow it down or break it. So if the customer is located far away, you need to work remotely. You need to ask your customer to do something and to send you their results. So the problem can be permanent or intermittent. So it can come up once in 3 months for one system, but for 1 minute. But during this minute, a huge backlog can be accumulated. So it can be fatal. Well, the problem can be not reproducible in test environment. So the final symptom can be reproduced. However, it has another reason, and it is even worse than a not reproducible problem at all, because you have to explain to your customer several situations, several reasons. So this is quite a complicated and dynamic system. We can depict it as a pyramid. I think we can use this image here. So the lowest level is the minimal measured elements, processes, tasks at the level of the operation system. So these are minimal units we can measure. They perform actions. They can input, output, they can sleep, and so on. So these elements perform certain functions and they interconnect with each other. They form data flow, they synchronize with each other, they compete for resources, they block each other. So this is the level of interaction. All interacting elements form an application. So this is a separate entity with its own performance metrics, and the customer will look into it and will form its customer experience. So judging by our experience, we can get successful results if we are well aware of all these layers. Only then we can obtain a good solution and a good result. So what's the problem? Obsolete utilities work at lower levels of the pyramid. So they tell us something about processes, their actions, but we cannot draw a conclusion about interrelations and application. So that's the problem. We need more advanced tools. If you're not acquainted with the application, which can happen quite often, for example, you are an Oracle specialist and your customer is a specialist in another field, so you will have to learn it so you can move from you can move top down or bottom up. You can learn tracing and so on. A couple of words about methodology. So it should exist. It's not important what kind of methodology you have, but you need one. So all of us are different. We have different way of thinking and of information analyzing. So you can select any methodology you like. Actually, in general, there are two approaches. There is a system-centric approach and application-centric approach. In the first case, we are focused on the system, on system metrics like the disk subsystem response time, cache size, and so on. And we check them against compatibility with some preset parameters. If something fails, we believe that this is the reason for our slow performance and we start improving it. So actually everything can be in trouble and processor can be overloaded and so on. So you will spend a lot of time on everything and will not get any results. So what is an alternative? So application-centric approach. You are focused on the application. You study the operation of the application. You analyze how it spends its time, and only then you turn to optimizing disks, processes, and so on. So in order for tracing to work, there should be some data source. So there are a so-called static and so-called dynamic tracing in the Linux. So static tracing includes trace points in the kernel. These are certain hooks you can hang something on. The same you can find in the user space. So in order for it to work, a developer should take care of that. So certain options should be there in place. So dynamic trace includes key probes. So these are some points in the kernel, in the middle of the kernel at the input or output. The same we have in the user space. So this is some information about applications so that we know where to put our probes. Except for tracing, we have PMUs. These are counters provided by processors. So in the operation system, we can see whether processor is loaded or free. So it's good for the planner to know about this. This is quite a complicated system with caches, conveyors, and so on. So we have to evaluate whether it is used effectively under the load. So The storage is getting faster and faster. It's working in the microsecond area, so we believe that bottlenecks will be moved from processor to memory. So these meters, these counters will be used more and more. So, so let's speak about tools. So the first one is ftrace. It has existed in the kernel for a long time. It's an embedded tool. So this allows developers to look into the kernel with the time passing. It acquired new functions. It can work with static and dynamic tracing. You can trace separate processes or the system as a whole, and data are stored in RAIN buffers at each processor. And for the user space, it is accessible from debug info in the network. You can find many scripts which can work with it, which can be connected, and from some rough traces can develop some easy to understand reports. So it's easy to use it because it is embedded. Of course, you need a debug info access, so you can suspect some problems and you can dump it to the disk, and then you can analyze it visually, which is easy for one or two processes, but difficult if you have many processes, or you can add some front end, or you can grab it. So the problem with ftrace for the task I wrote for the developers who have another task, they can view it differently. The problem is the lack of analytics, because we have to process these traces later on. So why do we lack it? Because we don't have any CPU profiling there. So profiling allows us to learn about some functions which require a lot of resources from the processor. So it's a kind of temperature measuring tool. We can use it to understand what kind of process is ongoing at the moment. So Perf is a utility which can be installed in Linux common tools. Initially, it was developed to enable access to meters later on, counters for PMU later on. It learned how to use static and dynamic trace points. So we can build static reports. We can process them using some external open source utilities. We have quite many such utilities. They can build beautiful maps and graphs, but for Perf it is especially useful. The advantage of Perf is the processor profiling. It can do backtrace and symbols stacks. So if you do your profile in the stack, you will see kernel space, user space libraries, and you can connect Java, Node.js, and other features, and it will work. So you will get a full picture. And in the case I described in the beginning, Perf is very useful for groups of processes, for many processes which eat up CPU, and you have to understand what they are doing, but you do not need to dig into the center of kernel. So this is a good example. Internal benchmark of NVMe subsystem. So when we switch on LVM, we have bad scaling and we have very high processor utilization. So we collected Perf for a bad and good case, so that we can simulated under our control. So in a good case, we see that processor time is equally distributed between many functions. So from the first sight, it looks fine, nothing to optimize. In a bad case, we see immediately kernel functions which eat up much processor time. We can see what they are doing, in which conditions, and so on. In this particular case, we saw immediately what was scaling badly. So it requires half an hour work. Next tool is SystemTAP. In comparison with the previous tools, it's programmable, so you can write a code in the embedded language in order to process trace points or k-probes. So SystemTAP compiles your code into dynamically loaded kernel. If the system is alive, right in the kernel, you can process traces, you can sum them up, you can see the context, aggregate them, put some conditions, and in the user space, you will not have many gigabytes of traces, but quite a small volume, just what you require. In SystemTAP, there are a lot of ready-made scripts, so you do not have to program, but you can choose some ready-made script. So the access threshold is quite high. So in order to use SystemTAP, you need to learn a lot of things. And in order to try something in user space, you need some access to applications. Moreover, it can be risky for productive environment. Here we have some contradictory opinions. Some believe it's a good and efficient tool, others believe it's problematic. So at the beginning, in SystemTAP, you have overkill working. So if you don't know how to use it, it's too much for you. However, if you manage to localize your problem, you restricted it to some particular kernel function, so you understand why a particular code runs in this particular way and not in the other. So then SystemTAP will be really useful for you. LTTG is an interesting tool developed by Matthew Denor, who actually wrote a thesis about trace points, and actual trace points themselves are his creation. And in Harbor, there is only one article about him with 5,000 views.
Well, some of the functions seemed very interesting to me, but in general, the algorithm is not that different. It's not programmable. You just set the profiling rules, the kernel module, build the traces, transfer them to the user space, and then the interesting thing begins. You may store the file in the CTF format, and then all the utilities that understand the common trace format are suitable for visualization, analytics. Yeah, that's it. So around the CPMG, there's a small ecosystem, which is good for such reactive troubleshooting, and the work with the application that you don't know is very useful. Well, besides the file storage, you may transfer the data on the network. If you have clusters from several nodes, you can transfer the traces into one and analyze the whole cluster from one place, from one point. You can also transfer the user space programs. You may review the statistics online. It's like on the run. And also there's an interesting function, flight record mod, when traces are permanently gathered into the buffers, and then in case of something, they're dumped on a disk. For example, the high latency of something, different options of latency. Then you get the previous history, several seconds of traces of what happened before the moment that is interesting for you. It's for seldom happening problems, mini hangs, etc. Without such options and functionals, such cases are really hell, when you can only do fortune telling. Well, TNG, it's very suitable, and if it's already installed at the customer, I wouldn't search for anything else. I would simply ask for traces to analyze. The cons. There's no CPU sampling. If it's not installed at the customer, I believe it will be difficult to get it installed because it's a different kind of software, and there's plenty of user space and components of user space dependencies. In the kernel, I've counted 42 modules from it, so it's too much. And not everyone will permit to use it. Also, for analytics, they use Python scripts, which are terribly slow. And while it's analyzing the traces, your customer will call you too frequently, asking for updates. The new subsystem in the kernel is the next tool, eBPF. Well, it's two components. eBPF is a virtual machine in the kernel which understands the bytecode and the toolkit for it. Compilator and front end on a Python on a Lua. Well, you can record processor from trace points, then the processor shall be loaded into the VM, and you will get functionality close to SystemTAP, dtracer, and you'll be able to process trace points right in the kernel, while you'll have less dead nerve cells. Well, also, SystemTAP may be ported to it from dtrace, from fprof, and you can find dozens of those in the networks. This tool is actively developed. The cons is that you need a fresh kernel to do even the simple things you need to do programming, and I've tried to use it with big high load, and I didn't get good results at profiling. It seemed to me that it's simply losing the traces. But it's actively developing and is becoming more and more mature. Now, the tool that I'd like to describe in more detail, this is LinuxKI. It was recently sourced before the year 11. It was proprietary. It Hewlett-Packard, and before that, it had a predecessor. It was called KItrace, and when HP-UX started to die and its engineers switched to Linux, they've noticed it's a convenient tool, so they ported it. This tracer has a fixed number of tracers. It may work with a couple of dozens of traces in the kernel, trace points. Only a limited number of those may be added or removed. The main thing is that they're dumped on the disk and analyzed offline or online. It's possible to do it online as well. In fact, why this approach was chosen, I have a theory explaining it. Initially, the team that was dealing with productivity, they were analyzing the crash dumps. What is that? It's like pathologists' work. You have the result, and you have to understand what caused this result. The other benefit, it's an interesting work, is that in this dump you have everything at the same time. You don't need to keep asking the customer to collect more information. The same approach was used for, well, at productivity. One may mention two main components of LinuxKI. That's the kernel model, which is loaded only for the period of the data collection. Then it's connected to the trace points and is sending to the user space. At the user space, there's one console utility called kinfo. It either stores the traces on the disk so that you could ask it from the customer and analyze at your place at the test machine, or when utility kinfo is making reports right on the way. So you start it, and in the system you are looking at different subsystems. If you've brought the dump LinuxKI into the machine, then with one script you can build all these statistic reports, plenty of those, and later analyze them. Or you can transfer the traces into the readable format, like ftrace, and then you just review it. Well, the ideology, the utilities. First of all, they're using application-centric approach. It's are created so that you analyze the applications and you collect enough information to give the answer to two questions. If the system is running, what does it do? If it's waiting, what is it waiting for? And instead of a long description, I'd rather provide you a real-time case. Here is an example. The Oracle is reporting high I/O wait times, while the disk subsystem latency is normal. The high system CPU usage, and we've collected LinuxKI dump for 20 seconds. And created a statistic report. Since the Oracle is cursing about input and output, we look at the Oracle DB writer and begin from the planner. We see that 98% of time in 20 seconds of traces, DB writer was asleep. It wasn't working. It was waiting. It wasn't running. Next, we continue and take a look at the sleep report. What was it sleeping about? With what stack did it get into the sleep mode? Well, you see this strange Oracle language, user spaces here, but we went into the sleep at the system call allogatens, so we were trying to do asynchronous I/O. Next, interrelated processes. That's via the sleep-wake-up mechanism or tool. Who did wake up whom? And we see that the DB writer interacted a lot with co-working threads. This is strange. Why? While trying to record the data on the disk, it did wake up due to a coworker. Doesn't say anything to us yet. We leave it and go further. Next, we check the CPU report or profile. We try to check what the DB writer was doing at the time when it wasn't asleep. Most of the time it was asleep, but some traces were caught. The problem is most likely not in the processor work. So we continue. In a different case, it would have been very useful. Now the system calls. I get there's a bit more details in this report. The system call, there was only one, and it lasted for 14 seconds. So we've made one US submit, and after that, for 14 seconds, we were waiting. Something must be wrong here. Now let's check the file system just in case. And yeah, it was a 18 kilobyte record in one data file. and it was hanging. So what do we know? Now, DB writers are waiting for something. They interact with co-workers, and now we look at the activity of the disk subsystem. Here we see that the response time is 16 milliseconds. There were just 91 operations, so they couldn't really record anything. So the problem is not with the disks. We expect something else. At this point, the only clue is that DB writer was interacting with coworkers. So in the same report, we choose one of the coworkers and take the same way. Have a look. We've just made it a bit shorter. The co-workers were also asleep. See the sleep report? See that co-workers were doing the flash request. They were trying to flash the cache storage, so they were doing the very writes. In this case, the customer understood that the storage doesn't support the debugger writes. They switched off, and so the problem disappeared. So in practice, the whole pathway took us maybe roughly 1 hour. And we received the result not by guessing, but following a logical path. We now understand who is waiting for whom, what the application is waiting for, and finally we detected the guilty subsystem. So the benefit of Linux is that it's simple to use. It's convenient for the customer. They have one script, they generate the dump, and they send it to you. That's it. So there's a high probability that you detect the problem. And you don't have to ask the customer for too many things. The data may be ported. You may assemble it in one architecture, build it in one architecture, and then you'll analyze it. And it has very good analytics. That's the strongest point of this tracer, the report that it generates. In most of the cases, it's sufficient to solve the problem. As for the cons, yes, you have to install the kernel module. Not everyone will let you do it, especially the cell operator, banks, they're very strict about it. You need the root privileges, and it generates a big amount of data. Oh, what happened? By the way, we're getting close to the time deadline. We're already eating up the time for Q&A. In fact, I was nearly finished. I'm sure they will revive the slides pretty soon. So while we're struggling with the equipment, maybe we can take some questions from the audience. Any questions? Yes. The audience is live. Sergey, tell us, please, why do you think the Thomas analysis with the help of a real-time processor tracer isn't kind of viable? It is supported for 2 years, but it doesn't seem to be viable. You never mentioned it, just PNU. Real-time what? Real-time processor trace, it's a feature, Skylink and higher, when a real-time trace is assembled of everything that happens. Oh yeah, tool-over feature, the new one. It's supported for 2 years already, but nobody's using it besides Intel. Why that? I don't know. I've read about it. It seemed interesting, but there are no real use cases where it could be useful. I just didn't have such cases, so I can't give you any comments. Any more questions? You've mentioned the tools. They strongly depend on the human participation. Sometimes it's a bit late due to that. Don't you think so? Well, common sense tells that you need to know to catch these things before the production, at the stage of testing. It should be automated. It shouldn't be manual. Can you specify, speculate on that? So that less manual work is necessary, and so that you could catch the errors before the production time. Well, the problems I described are not standard cases. It's when something already went wrong, when the local company experts couldn't clarify, so they go either to the vendor or to somebody else. So these are non-standard cases, exceptions anyway. And I don't think such cases may be detected automatically. These are the cases when human participants is necessary, and the task of the tool is provide enough information for a human being so that he can solve the problem. Hope I've answered this question, your question. Yep. More questions? Sergey, thanks for your presentation. Tell us, please, which of the mentioned utilities you would use for the analysis of the network subsystem as an option to analyze what the open switch is doing when most of the work is happening on the level of the kernel without the exiting to the user space. BP, perhaps I would go there, or Perf. BPF or Perf. So LinuxKI is not suitable for that. No, no, no. It's not suitable. It's not about that. When you need to go in detail into a certain subsystem, it's better to use a different tracer. LinuxKI is if you have problems with applications, not with the kernel subsystem. Yesterday there was a presentation by Alexander Komarov on this topic in this hall. You may find him and ask him. Sorry, the mic is not working. The interpreter. Hello, Alexei. How cheap is it to use the LinuxKI at a highly loaded systems? Perform, it's cheap to profile it. LinuxKI is cheap as well. Cheap because it's hung on a small number of traces. It was initially planned for high loads. It was used to fix to superdomix when it was fully loaded. If you take a look at the Hewlett-Packard white paper, 16 socket super house with, I think, 10 kernels at a full load, it works okay. Thank you. So, at this optimistic